Good morning. Please don't. Oh, sorry. Please don't forget to sign attendance and an honest warning in advance. I will check attendance more than once. You know why, several of you. Our current schedule or plans for the nearest future. Here we have, here we have let's say the first information next time is the unit test because today we finish with the sixth unit. Yes, next week we only have two lectures for the seventh unit for functions of several variables. That's right. And then next Friday you have the second midterm, where I could say second half term, but it's very easy to say midterm one, midterm two, even though this is end of term, this is not really in the middle, but it's half. It's the second half. So in that unit test, you will have one task for, well, two functions, monotonicity and extrema, which means investigating functions will be done by little parts separately so that when you make a small mistake at the beginning, you don't spoil all your work, right? So monotonicity and extrema, that would be one of the tasks, two functions like that. Then you will have one task about the greatest and least value on a segment, finding the greatest and the least value of a function on a segment. Concavity and inflections, remember that was about the second derivative, all about the second derivative. If we talk about the first one, about the first task, monotonicity and extrema, because you also have to find the intervals of increase and decrease, it's probably more convenient to use the first derivative test. But if any of you prefers to use the second derivative test and can deal with it, well, then I have absolutely no objections, of course, if all the answers can be provided. And finally, asymptotes. Asymptotes. So you will not have the full investigation, you will not have to graph a function in the test, but these elements of investigation, how to establish some facts about functions. That's your unit test for June, for the 4th of June for Friday. Now, today, as you remember from last time, we had this topic, finding asymptotes and the overall plan of investigation of a function, which involves all of the above. All of the above. As you might remember, we did not have time to investigate functions last time, but I did give you the plan. Now, a very quick revision of what we did last time, what was new. Finding asymptotes was a very, very huge, important part of last lecture. So first of all, the easiest, of course, to find were the vertical asymptotes. X equals A is the equation of a line. I would like to remind you that we write equations of lines. Remember that an asymptote is not a number. An asymptote is a line, so you have to write an equation of a line, not just the number A. But on the other hand, they are fairly easy to find if the function is rational. Those would be the potential points for vertical asymptotes would be the points where the function has discontinuities, the function where you have to divide by zero, those type 2 discontinuities. And basically this means if you have a vertical asymptote, when x approaches this point A from the right or from the left, the function value tends to infinity, either positive or negative. So the vertical asymptotes can be recognized as those points at those points on the x-axis where the function tends to infinity. So these are basically, if you look at the domain of the function, the points of discontinuity, the points of discontinuity, the points where these infinite gaps happen. And then we had slant asymptotes. The slant asymptote, of course, is a line. You know the general equation of a line, the point slope form. Not the point slope, sorry, the slope intercept form, y equals kx plus b. Because we are in calculus, we prefer to use the line equations in the function form as functions. Y equals a function some expression of x. You remember that in analytic geometry, we had different ways of writing down an equation of a line because we are in calculus, and in calculus we view y as dependent on x. We write the asymptotes in this form. So how to find these values? The coefficient k can be found if you divide the given function by x and look at the limit when x tends to infinity. If this is a real number, then we go on and find the coefficient b by subtracting function minus k times x. K is what you just found. Please note that here we do not divide by x anymore. We divide by x to find k, which is the reason why you had similar expressions in elementary mathematics, because it is important for calculus. And then don't forget to subtract. If k is negative, then you will see a plus sign here, of course. And if this number also exists, so if both these are real numbers, then you have your asymptote. And of course, in the end, you have to write the equation of the asymptote. If k is 0, again, something you should remember, then the slant asymptote becomes horizontal. Slope is 0, so we basically get y equals b. Horizontal asymptote. If you are clever enough to recognize the situations where the slant asymptote becomes horizontal, both of them at the same time in the same direction are impossible. However, of course, in the positive and in the negative infinity, you might have one of each, but not both in the same direction. So horizontal asymptote, if you are clever enough to recognize, in some cases, not always, but for example, in rational functions, where you see that the denominator and numerator have the same power, then yes, you should be able to recognize that the graph must have a horizontal asymptote and prove it by simply showing that the limit is the number b. The limit of the function is the number b. Evidently, if you divide by x, then the limit will be actually infinitely many times smaller, that is, it will be 0, which connects to this, the horizontal asymptote. So if the limit of the function itself is a number, horizontal asymptote, then when you divide by x, which tends to infinity, you get the coefficient 0, the slope 0. And of course, it could be in either direction or both at once. So in principle, it is perfectly sufficient, as we saw last time, to find vertical and slant asymptote, to look for vertical and slant asymptote. However, if you notice that it is possible to do a shortcut, if you see clearly that it is possible to do a shortcut and find horizontal asymptote without messing with these less than pleasant limits, then by all means do it because it's helpful. And so some examples. So I think we had a look at this example. We already saw that this function had a vertical asymptote. X is 1 because for the domain we see x cannot be 1. We have to divide by 0 then. So that's vertical asymptote. In principle, if you see the discontinuities at the domain, then it might be enough to write vertical asymptotes in the simplest functions. In more complicated functions, you would have to check the one-sided limits in the suspicious points, in the suspicious points. And then we see that we have x and x first power, both in numerator and denominator. From that, we conclude that there might be or should be a horizontal asymptote. We just prove it, we just establish it formally now. We had to write when x tends to infinity of the function, in this case 3x minus 4 over 1 minus x. We saw that this limit equals 3, so the horizontal asymptote is y equals 3. Vertical and horizontal asymptote. Two lines, vertical line and horizontal line, which would make it easier to actually sketch a graph of this function. And well, if we have time, we might even attempt to do this with a simple situation. Now this one is something somewhere where we did these limits. If you remember, we had k as the limit. I am not going to show the full computation because there's simply not enough time for that. Limit of f of x divided by x. So that means that the exponent, the power of the denominator increased. If you do it correctly, you got 1, and then b was actually limit when x tends to infinity. We had this function minus 1x, or simply x. When we pulled this together on the same line, on the same denominator, we saw it was, I don't remember, 3, 2, 3, I think it was 3. I'm not perfectly sure, but I think it was 3. My memory serves more or less. So it might be a mistake. I might have made. I might be mistaken here. I don't want to bring up my notes at the moment and check once more. So the slant asymptote for this, was 1x plus 3, x plus 3. I would say something, or minus. I think, no, it was plus, I think. And of course, this also has vertical asymptotes, because from the domain we see x times x minus 3, the denominator, cannot be equal to 0. So the vertical asymptotes would be x is 0 and x is 3, those dangerous moments. So this is what we did last time. Now, what we did not do this, and we did not do this. We have two functions which I said, let's skip this. However, we could try to establish these things. When x tends to infinity, evidently, what we can see, division by 0 is impossible. So perhaps we might have a vertical asymptote. Maybe we might have a vertical asymptote, this, but we have to check, because in this case it's not obvious. Because in this case, you see this particular function, you see what it looks like. It's not a rational function, it has trigonometry involved, so we cannot be perfectly sure, which is why we need to look at the limits for vertical asymptotes as well. So the limit when x tends to, sorry, not one, I'm very sorry, at 0. When x tends to 0 plus 0 from the right of the function, 2x minus sine x over x. We see when x tends to 0, we have 2 times 0 minus limit of sine x over x when x tends to 0 from whichever side. This limit is, as you should remember, is 1. So it looks like it's actually minus 1 when x tends to 0. When x tends to 0, this limit is 1. This limit is 0, more or less. So we have minus 1. It's not infinity. It's not infinity on the right-hand side. So maybe there's no vertical asymptote in this. We see that the function from the right, somehow when x tends to 0, it approaches the value minus 1. Somehow. I don't know how exactly. I don't know what the graph looks like. But we see that there's no asymptote. And on the other hand, if we have x tends to 0 minus 0 from the left, we still have the same. So f of x, we still have 2 times 0 is 0 minus limit of sine x over x when x tends to infinity is minus 1. So it looks like we don't have a vertical asymptote because from both sides, as you see, the function value tends to -1 when x tends to 0. So no vertical asymptote, no vertical asymptote. Because you see, when we check the limits, it's not type 1, sorry, it's not type 2 discontinuity, it's type 1, removable, by the way. So the slant asymptote, on the other hand, let's check the slant asymptote. What happens to that? So k, if it exists, when x tends to infinity, the vertical asymptote is the only asymptote where x tends to number. For slant and horizontal asymptote, x actually tends to infinity. So we have to check whether that slant asymptote exists. Let's divide the function f by x. So we have limit of 2x divided by x is 2 minus sine x divided by x and divided by x again. So this is f of x divided by x. And we see that when x tends to infinity, 2 tends to 2, and this other one, sine x over x and divided by x again. As x tends to infinity, you might think that it is something like 1 again, but please note, x tends to infinity. X does not tend to 0 now. X does not tend to 0. So, not 0. So this is not 1. But let's remember, sine x is bounded. It's always between -1 and 1. However, x itself tends to infinity. So this limit actually is 0. We had a look at this kind of limit. You could also use the squeeze theorem or the sandwich theorem for this. By replacing sine x by 1 or by -1, you will still see this limit is 0. So zeros on both sides. So k is 2 if b exists. If b exists, k is 2. Now let's check b. So you see, it's not always very obvious. It is usually obvious for rational functions. For functions where we see simply a quotient of two polynomials. For those, these asymptotes are obvious. For the others, unfortunately, not so much. So b is the limit when x tends to infinity. Again, let me remind you, infinity, not 0. 0 was only for the vertical asymptote, and it could be any other number if it's a dangerous number, a dangerous point. But for the slant asymptote, for the horizontal asymptote, we are going horizontally to infinity and see what happens. So we see 2x minus sine x over x, that is f of x, minus kx. K is 2, so minus 2x. We see that these two disappear, and now we see that b is, in fact, we see when x tends to infinity, we again have the 0 limit because sine x is bounded and x tends to infinity. Sine x is bounded, that is, its values are finite and small, well, finite values, and x, of course, tends to infinity. So we still have something smallish between -1 and 1 divided by something infinite. So, of course, it's 0. of course, it's 0 by the squeeze theorem. So we see that this limit b is 0. So it looks like we have a slant asymptote y equals 2x plus b, which is 0. So y equals 2x is the slant asymptote of this function. So basically, we can imagine that no matter how the function, and this function behaves actually, no matter how this function behaves actually, in the infinity, it will approach this line. Again, it will do something here. I don't know, maybe it does tend to -1. Well, it does. And whatever it does, in the infinity, it will finally approach this line. In the infinity, this would approach this line. Actually, I have a feeling that it would fluctuate about this line. So like oscillating around this slant asymptote, because you know sine function is periodic. It does oscillate. So that would mean that probably this function, this graph, would also oscillate around the asymptote. I am just hypothesizing at the moment. It can be checked, of course, using any graphing calculator, any function graphing program. You could actually check if you are curious about what the graph looks like. So at the moment, I'm simply pointing out that at this point, the function might not be defined, but it tends still -1 when x is 0. Then it might do all kinds of things in the nearest region, nearest neighborhood. But in infinity, it will actually tend to this line, to this asymptote. No matter what happens here, no matter what happens here. And in a similar mode, it is possible to investigate this number 4. This investigation actually is demonstrated in the lecture transcript, so let's not spend too much time on this. In the test, in the examination, you will not get these very complicated functions. More likely, rational functions. In the homework, you have to see how to do these limits. You have to investigate. Now, finding the asymptotes, so we could see fairly quickly. First of all, notice x squared in the numerator, x squared in the denominator. This means that this function has a horizontal asymptote, not slant. So horizontal asymptote, we can check the limit of this function. Okay, x squared minus 1, x squared minus 4. When x tends to infinity, remember we factor out the square, or easily just divide the square out immediately without rewriting. So 9 minus 1 divided by it, 1 minus 4 divided by the square. So this limit is 9 when x tends to infinity. The horizontal asymptote is y equals 9. So it would be a horizontal line. And the vertical asymptotes, we see that the function is not defined at the points where x squared minus 4 is equal to 0. For a rational function, this is perfectly normal. So we have vertical asymptotes at -2, x is -2, and x is 2, two vertical asymptotes. So horizontal asymptote and 2 vertical asymptotes. This is comparatively easy to find. For this type of function, definitely so. And I'm not going to give you something, let's say, more complicated than a rational function in the test or in the exam, because evidently the time is not enough to do a proper investigation. That's why you have the homework. Another one. This situation, okay, let me see. B. Oh, okay, I decided to use B after C. That's correct. The order is that, exactly. So again, finding the asymptotes. we see that x squared plus 9 is never equal to 0 for all x values. Never equal to 0, it's always positive because x squared cannot be negative, right? So there's no vertical asymptotes. No vertical asymptotes because this limit will not actually be infinity when x tends to any specific number. If x tends to any specific number, you will see that the limit of this will also be a specific number. You will never get division by 0. No vertical asymptote. Horizontal? No, because the exponents, the powers, are different and the greater power is in the numerator. So let's check for the slant asymptote. Let's check for the slant asymptote. K is the limit when x tends to infinity of function divided by x. X cubed over x squared plus 9 divided by x means, remember, multiplied by the reciprocal. So now again, we can divide out. We can divide out x cubed, so we have 1. And here, please note, you do not divide out x cubed from this and from x. You divide out x cubed from the product. So x squared times x is x cubed divided by x cubed, 9x divided by x cubed. You don't divide out from each of the factors. If you have difficulties, then open the parentheses. It does complicate things enough a little bit because it's messy, a little bit messier, the algebra part. But you have to remember, if you have a product and you are dividing out some factor from a fraction, then do not divide each of the factors of that product. Split that divisor among them. And so we see 1 divided by 1 plus 0, that is 1. Of course, k is 1. Now, b is limit again when x tends to infinity of function as it is, without division now, minus 1 times x, kx. So evidently, to bring everything on the same denominator, we need to find the common denominator, which is of course x squared plus 9, x cubed minus the extra factor. You must multiply extra by x squared plus 9. So we have minus x times x squared plus 9, which is actually what you saw here. You had to multiply these as well. Limit x tends to infinity, x cubed minus x cubed minus 9x divided by x squared plus 9. So these will cancel out. Here we see that the power is greater in the denominator. This means that this limit should be equal to 0. You can find it by whatever method you like, infinity over infinity, even here, even using L'Hopital's rule. So we could say we could use L'Hopital's rule because it's infinity over infinity, no problem. And so we would have limit minus 9 over 2x when x tends to infinity. That is, of course, 0. You might notice that sometimes L'Hopital's rule is very convenient, both for simple limits, where we have infinity over infinity, and also for, let's say, not really complicated functions, but more sophisticated functions like trigonometric, exponential, logarithmic. For very complicated expressions, it might also get complicated again. So we have to be very, very careful with L'Hopital's rule. Because when you study it at school, please note that high school material is not as sophisticated as university material, and you might be shown only the simplest cases, the basic cases. So L'Hopital's rule is not so universal as to use it everywhere. But back to the slant asymptote. So the slant asymptote is y equals k is 1, so x, b is 0. So the slant asymptote is this, y equals x. No vertical asymptote, only a slant asymptote. We will have a similar function today, and you will see how this works. We will have a similar function to investigate. Now, okay, I hope I was talking long enough for you to copy things. And I seriously do hope you are taking notes and following, because if you don't write, if you just stare at the screen and get bored and then leave and whatnot, then you don't learn anything. Basically, you learn by doing along. Unfortunately, I would be very happy to get you right on my screen, but that takes some equipment, some devices. For example, it takes a tablet with a stylus. So I would be, of course, very happy if I could let you do some of the work and discuss. As it is, I have to do it here. Unfortunately, the sad consequence is that about half of you don't listen at all and don't take notes, and then they whine about you know what. Okay, in this case, I wanted actually to show another method for finding the slant asymptote. Does anyone have any idea? So we have vertical asymptote, very obviously, x is 2, because x cannot be 2. This is very, very obvious. This is immediately obvious. So we don't have to write any justification for this. Okay, we can write, because x minus 2 cannot be 0 from the domain. That's why we have the vertical asymptote here. For rational functions, this is enough. For rational functions, that is quotient of polynomials. Now for the slant asymptote, it could be also possible. So remember, the slant asymptote is the line which is approached by the given function. So in principle, if we could see what that line is without using those limits, it's not always possible, but in cases like this, it's actually very interesting and it works. Let's change the function y. Let's separate the polynomial. This is an improper fraction. Improper because square is a higher degree than a linear function. So it's an improper fraction, and it can be solved by, for example, by manipulation, but it could also be solved by polynomial division. Now, if you studied polynomial division at school, then this is what you could do. This is what you could do. So we could say 3x squared minus 4x plus 3. I will be using my notation. I know that in principle you many of you might have learned this notation where you write the divisor here and the quotient up there. This is acceptable if you know what you are writing. This is acceptable. In general, I am doing a compromise between the notation to which I am used and the notation, let's say this. So I am writing it like this. So I write the divisor here and the quotient shows up here. It's everything is together. So it all depends on how you are used to doing this. This notation, this type of writing down long division, I have no problem with it. If you prefer, if it's more comfortable, convenient for you. And so remember how we divide polynomials. When we divide polynomials, first of all, we must be sure that we have all powers represented. If one power, for example, x is missing, you have to write plus 0x, so that it's similar to long division of numbers. And then we compare only the first terms. So 3x squared, attempt to divide by x. 3x squared divided by x is 3x. That seems pretty clear, right? Now, to find the remainder, Like with numbers, we multiply 3x by this and write it below. 3x times minus 2 is minus 6x to subtract. Now we will be subtracting, like you do with numbers. For example, if you divide 7 to 7, if you divide it by 5, for instance, what you get in a similar way, you get 7 divided by 5 is 1. Then you multiply 1 by 5 and write it below 7 in order to subtract. You get the remainder 2. Well, sometimes, of course, at this point, you should be compacting this, abbreviating it. But how we think is this: then we bring down the next digit. Now we try to divide by 5 this number. We do exactly the same thing here. So I take this, multiply by the first, I take the divisor, multiplied by the first term of the quotient, write it below, subtract to find the remainder. That is, of course, this will always disappear, minus 4x, minus negative 6x is plus 2x. Then I bring down the next term, plus 3, and I think now, okay, now I am, in this case, I would divide, for example, 22 divided by 5, that's 4. To find the remainder, I multiply 5 by 4, right below, subtract. Bring down the next number, divide by 5 is 5, multiply 25, subtract. The remainder, the final remainder is 2. So I think, okay, so 2 divided by 5 is simply 2 over 5. It's simply 2 over 5. So I'm actually using the remainder to get the fraction part. We will do exactly the same here. So 2x plus 3 divided by x is 2x divided by x is 2. I multiply back to find the remainder. So what I actually divided was 2x minus 4. So 2x minus 4 would be the perfect quotient 2. And now subtracting, remember we always have to subtract the remainder 7. So I have to write plus 7 that could not be divided to the end. So I see that my function, this function is actually 3x plus 2 plus 7 over x minus 2. I divided out the polynomial. Just like here, if you have 7 to 7 over 5, dividing out the integer, you have 1/4, and then, of course, 2/5 when you are turning the improper fraction numerically into a mixed number. Here we do exactly the same. The one thing is the trick of dividing polynomials. I am not saying that everybody can do this, but maybe some of you have studied polynomial division at school, and now this is enough to remind you what happens. Now for our original task. So if the function is now transformed to this form, it's still the same function. It's simply rearranged. So when x tends to infinity, see what happens? When x tends to infinity, 7 over x minus 2 tends to 0. So the function value, actually, this approaches the value of this expression, 3x plus 2, which means, evidently, because 7 over x minus 2 tends to 0 when x tends to infinity, the function, the slant asymptote is y equals 3x plus 2. As I said, this does not work always. But sometimes when you see it would be comparatively easy to divide, it's possible. But please know the asymptote should be a line. If you get a higher power here, then there's no asymptote. Remember that you must be sure that this is an equation of a line. If this is not an equation of a line, then there's no asymptote. no slant asymptote at all. So always must make sure that this has to be a line, has to be a linear function. And before someone asks, but why can't we have other asymptotes that are not lines? Yes, in mathematics, actually, it is possible to consider asymptotic curves. That is a simpler function that can be approached by the given function. But that is something that you might discover in Mathematics Part 2 next semester. Although they might not phrase it like it is, but sometimes we could say, okay, this function is close enough to that fifth degree polynomial, for instance. So that's approximation, approximating functions. That's possible. Now finding the asymptotes and investigating the function some more. So remember this. Perhaps when x, evidently there is horizontal asymptote. If we had only the arctangent function, I am reminding you what the arctangent function generally looks like. Because it's x over 2, it might be a little bit more stretched out horizontally. More stretched out horizontally. But arctangent function generally looks like this. But here we have 2x plus this. So evidently, there is no vertical asymptote because the function is defined for all values of x. So we might want to discover the slant asymptote, which means the coefficient k is limit of divide this function by 2, similar to what we did before. Remember that with the sign of x divided by x. We do exactly the same thing here, very, very similar. So function divided by x, that is 2, plus arctangent x half divided by x. So now remember that first of all, the first term, the limit of 2 is of course 2. Now arctangent of x squared, x divided by 2 over x might be best to find using L'Hopital's rule. You can always do that. Now it is perfectly acceptable. It was not acceptable in the unit test number 4. After that, in the other parts, it's perfectly fine. So for those who love L'Hopital's rule, but it was interesting that they could do L'Hopital's rule, but they don't know differentiation. That was really funny. But okay. Okay, so we could see that arctangent actually, when x tends to infinity, arctangent tends to, remember, pi half, plus or minus pi half. So in this case, L'Hopital's rule is actually not necessary. We can use L'Hopital's rule only for infinity over infinity, or 0 over 0. Here, arctangent, when x tends to infinity, arctangent tends to plus or minus pi half. And if you divide by infinity, number divided by infinity is 0, so the k value is 2. So k is 2. Now to find the v value, remember in v one more time, and this is the last time I'm doing this because we need to move on to investigations. 2x plus the arctangent of half x minus k is 2x. So these again, you see how they cancel out very nicely in this case, and we have the limit of arctangent. When x tends to infinity, it is plus pi half. If x tends to positive infinity, and minus pi half if x tends to negative infinity. So in principle, we have two slant asymptotes. In fact, we would have something like, okay, the first asymptote, y equals 2x plus pi half, and 2x. So in the positive infinity, this function would approach this line, but when x tends to negative infinity, we would have y is 2x minus pi half, the second slant asymptote. That is minus pi half approximately here, so it would go like this. And the graph itself evidently would do something here in between, but it would in the end approach one line and the other line. So the general idea, I'm trying to show you not only how to establish the equations for asymptotes, but what this means, so that it's easier for you to put things together. And now finally, let us put things together. Investigating functions. So I'm reminding you very quickly of the plan I gave you last time, and it's also in your lecture transcript. So basically, we start with things, usually investigating things that do not need the derivative. So if the function is obviously odd or even or periodic, that's less likely, but odd even, if you see the function is very definitely odd or even, then you should note it. You should write it down because it can be used to your benefit. Domain is the first thing always. Zeros and y-intercept, that is, all the intersection points with the axis of coordinates, you'll find it by inserting x is 0 for y-intercept and y is 0, finding x for the zeros of the function. Asymptotes can be found at this moment, or asymptotes can be found later in the end when you are attempting to graph the function. This could be left also for the end. The plan, like 1, 2, 3, is not strictly defined. However, if you see that the function is odd or even, then finding 1, 0 automatically gives you another one. So that might be the best order. 1, 2, 3 is definitely the best order. Asymptotes can be found at any moment. Then we do first derivative and explore monotonicity and extrema. Then we do second derivative and explore concavity up and down inflection points. Finally, we graph using all this information. And now let's just try it. So let me check the time. All right, it's not so bad. 45 minutes approximately. That's good. So we need to graph. Basically, I want 3 functions. I think if we have enough time. 1, 2, 3. That's it. Yes, that should be enough. That should be enough. And I should go back from the current slide and go back. Okay, there we go. This is a simple cubic polynomial, but it is very good to, again, to remind you how this investigation altogether goes. So the first thing to determine is, of course, okay, without asymptotes, yes. That's right, without asymptotes. So the first thing to determine is the domain. The domain is the set of all real numbers, because this function is defined for any value of x. Next, odd, even, periodic, definitely not, but we could see these are both odd powers, so we see that the function is odd. If you have doubts, you can always check f of minus x is 3 times minus x minus negative x cubed, which is minus 3x plus x cubed, which is, take minus outside, 3x minus x cubed. You simply verify, we simply verify that if you put minus x instead of x, the function simply becomes its own opposite. That means this is an odd function, which is very useful because that means we can always think about this central symmetry, symmetry with respect to the origin, we know already the graph will be perfectly symmetrical with respect to origin. So we can explore, for example, this function for positive values of x, and then just get the symmetrical statements for the negative values of x. That's useful. The next thing is zeros and intercepts. So if x is 0, then y is 0. So we have 1 point, 0, 0, through which this function, this graph passes. The second one, if y is 0, we have 3x minus x cubed is 0, x times 3 minus x squared is 0. So we see that the x-axis, so this is with y-axis. This is with y-axis. Now here with the x-axis, we see x is 0, so that's the same origin again. And then we have two possibilities more. X is positive or negative square root of 3, if the second factor must be equal to 0. So we have root 3, 0, one intersection point, and negative root 3, 0, the second intersection point. We know that root 3 is approximately 1.7 for the purpose of graphing. For the purpose of graphing, we can actually estimate it approximately. This is not elementary mathematics. You may use a calculator to do an estimation. All right, so this would be with the x-axis. Now, asymptotes, no asymptotes, so let's go on and do the derivatives, which are simple to do. So, no asymptotes, but let's do the first derivative. The derivative is 3 minus 3x squared. That's 3, 1 minus x squared. And we, of course, understand that the critical points, stationary points are 1 and minus 1, because if the derivative is 0, then we get the stationary points. Now, the sign diagram, let's remember the sign diagram. We see that the stationary points are minus 1 and 1 on the x-axis. So this is where the derivative is 0. The tangent line is horizontal, and then we can check. If x is very large by absolute value, then 1 minus x squared will be negative, both for x is 100 and for x is a minus 100. However, for very small x values, 1 minus x squared will be positive. I am reminding you that in investigation and in this upcoming test, the sign diagrams are important. I will require sign diagrams. I actually am putting the requirement for sign diagrams into the test tasks. So you have no excuse not to do that. Minus, negative, decreasing, plus increasing, minus decreasing. So we have evidently a minimum point at minus 1 and a maximum point at 1. It's easier to find the value of positive 1. 3 minus 1 in the original function, please, not in the derivative. In the original function, 3 minus 1 is 2. Because of function being odd, we are using the symmetry with respect to origin. So this means that here the minimum value will be minus 2 because it's odd. So it simply helps you to find the values. It helps you to find some points. Okay, now I'm leaving this here and moving on to the second derivative. So I am recapping something. So the first derivative was 3 minus 3x squared. So now the second order derivative is minus 6x. So the critical point, we don't call it stationary because this simply means a critical point where the second derivative is 0. Then that means that we have this critical point at x is 0. Now I am going to do, okay, critical point 0, second derivative signs. If x is positive, second derivative is negative. If x is negative, second derivative is positive, which means the function goes happy and then sad. So we have an inflection point. We already know 0. X gives us 0, y value. Now I am putting this together. I am putting this together with the first sign diagram or the information or with the information from the first derivative. In the first derivative, we have critical points -1 and 1. Look back. Decrease, increase, decrease. Go on. So I am doing decrease, increase, decrease, right? Now I have this information, and also I remember that we had a minimum at -1, -2, and the maximum at 1, 2. This is simply a reminder. You don't have to write everything twice in your homework. It's simply because I don't want to keep skipping back to the previous page. I'm simply copying it to this page so that it's a reminder from the previous. It's a reminder from previous. Now we see very clearly. We can mark the interesting points. Let's see. Our interesting points are, first of all, the intersection points with the axis. This is the origin. This is the x-axis. This is the y-axis. And please note that the system of coordinates must be established. That means you need the positive directions, you need x, y axis marked, labeled, you need 0, and you need to see the scale. You need to see where the point coordinates are actually. So we see that the interesting points have values, coordinates like 1 and 2, nothing really more. So we can choose a fairly large scale. So I would say this is 1, this is 2, this is 3, this is 1. So that you choose the scale on the axis at the moment, when you see the coordinates of all the critical interesting points, let's put them interesting points or special points or significant points, when you see the numbers that are present in our investigation, you know what scale to choose for the graph. And so now, okay, 0, 0. Then we had the intersections with the axis at also at plus minus square root of 3 and 0 on the x-axis. So 1.7 approximately. This is 1.75, so it would be somewhere here. Square root 3, approximately 1.7, and negative square root 3, approximately here, negative root 3. So these are the points where the, oh, sorry, I did the wrong spot. Eraser, wrong. Goes there. This is negative root 3. So these are the 3 points where the graph intersects the axis. Now, the maximum point is 1, 2, 1, 2. Let's just check the, sorry, someone. Okay. That's again something that should not be there. Messed up a little bit. All right. Okay, sorry about that. So the minimum point, -1, -2, that would be, this is the minimum point. -1, -2, this is the minimum point. And 1, 2 positive values is the maximum point. 1, 2. And then we have this inflection point at 0, 0. So this is inflection. At this point, we have inflection, this one. Now, let's see. Function decreases, 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 being concave up until it reaches the minimum point. So basically, we understand that the function decreases, being concave up until it reaches the minimum point. Then it starts increasing till the inflection point, as we say, still staying concave up. So it's still staying concave up. Now, after the inflection, it goes on increasing. See, that's why I was putting these two diagrams together. It goes on increasing, but now it becomes concave down. And then after it reaches the minimum point, remember that at this point there's no peak. The tangent line is horizontal because the derivative was 0. It reaches its maximum point, goes down, still stays concave down. And of course it has to pass through this point. Okay, not very accurate. I am doing it with a dotted line at first because I am just constructing this, and afterwards I can retrace this now with a full line, of course, to make this more accurate. To make this more accurate, basically we know only 5 points on the graph. If we wanted to be more accurate, we could also check some extra values. For example, if x is 2, the function is 6 minus 8 is minus 2. So if x is 2, the function value is minus 2. Well, yes, this is, as you see, this part at least is accurate enough. And if x is minus 2, then the function value is evidently plus 2. So I can make some corrections after I find some additional points, some extra points. I could try to find, for example, when x is 1/2, then that will be 1.5 minus 1/8. That is 1 and just a little bit less than half. And that's a bit less than, should be thinner, evidently. Should be a bit thinner. So you can find some extra points if necessary. Plot extra points if necessary. So only if needed, extra points. And then when you have the number of points to your satisfaction, you can trace the graph now fully, completely, make it completely obvious, completely evident. Again, and next graph. So any questions about this? Looks like no questions. All right, let's see. Just a moment. All right. Use Desmos for to save time. To save time for what? For teaching understanding? For explaining how these points work? I don't need anything to give me the graph immediately. I can use any graphing software. To save time to get the graph perfectly and then zoom in to the appropriate accuracy. That's, of course, that goes without saying. What I am doing here is I am trying to teach you and then check your understanding. 3 people out of the whole group maybe have a previous understanding, but the rest need to be shown it everything like counting on fingers. Sometimes it's just necessary. So yes, of course, for practical purposes, you use whatever you want. That's not a problem. Okay, now let's go on to the remaining things. Investigating and graphing. This function is without the second derivative, because the second derivative and inflection points would be a little bit pointless. You will see. And so this graph, let's check First of all, the domain, correct color. So the domain, we see that x is not 3. That reminds me, okay, that will be a vertical asymptote at some point. Have to remember that. Now the second part would be odd or even. Looks like this is neither odd nor even. We can see that the denominator will become something completely different. The numerator will change sign. Well, sorry, will remain the same. The denominator will become something different, not the same, and not changing the sign. So this means this is not odd and not even. So this is, let's say, a function in general, neither odd nor even. Now the zeros and the y-intercept. So if x is 0, then y is 0. So this would be the y-intercept. And if y is 0, then we see x is 0. Again, nothing else. The same. So there's only one intersection point with the axis. Only one intersection point with the axis. But yes, let's remember we have the vertical asymptote. So let us do the asymptotes at this moment, at this point. Let's do, okay, we have vertical asymptote, obviously, when x is 3, at x is 3, and the powers are not the same, x squared and x. The powers are not the same, so we can do a slant asymptote. It's not horizontal very definitely. So for the slant asymptote, if you like, you can use the division, you can use whatever other methods you like. I prefer, well, I would do it for the sake of change, for the sake of, let's say, really for change, to have something different. I will try to divide without really dividing. X squared divided by x minus 3. X squared would be divided by x minus 3, would be divisible if we had x squared minus 9. Because we know this is the square of the binomial, x plus 3 times x minus 3. And then I add 9 back. So I see that this part gives me x plus 3, and this part 9 is not divided. And from this, I conclude that if x tends to infinity, then 9 over x minus 3 tends to 0, which means the slant asymptote is y equals, and that's not the function, it's the slant asymptote is x plus 3. This is also something you can do. If you find manipulating the expressions easy, then this is a very effective method because it's very, very fast. If you can see your ways, if you can see your way to doing this, those who are very good at mathematics definitely can. This works very nicely. If not, then, well, and in some functions, not in all functions. But if you can see this, if you can notice this, I have no objection to that. So now we have a vertical asymptote. We have a, okay, this is again the same thing that happened previously. The reason, I understand now the reason for it. All right. So what we can do, I will go there. I will already sketch those asymptotes. I will already sketch those asymptotes in, let's say, red, no problem. So one asymptote, the vertical asymptote, x is 3. X is 3, that will be this vertical asymptote. Then we had the slant asymptote, which was y equals x plus 3. Okay, x plus 3, let's say this is 3, this is 3, this is 1, this is 0. So marking the scale, definitely, because otherwise we have problems. So x plus 3, that will be this line. So we have a horizontal asymptote and a vertical asymptote. I have a suspicion that this is not very good because it will be very difficult to see part of the graph. It will be a little bit difficult, yes. Part of the graph would be a bit messy. So we might need to decrease the scale. Now the derivative, the first derivative only. The first derivative only. Again, for the derivative, you could use this x plus 3, and what was the other one? Go back, check 9 over x minus 3. Plus 9 over x minus 3. To differentiate, you will have 1 plus, and then it's x minus 3 squared, and here we have minus 9. Remember, 1 over v derivative, so some of you at least some of you might remember. Others will use the general quotient rule for this function, no problem. I prefer to simplify things as much as possible. So negative v derivative divided by v squared. So this can be done. The problem with this is, of course, that it might be a bit difficult to find the critical points. But let's see. The critical points happen if, of course, 9 over x minus 3 squared equals 1. So that means x minus 3 squared equals 9. So that means x minus 3 equals positive or negative 3, two possibilities. So either x is 0 or x is 6. So these are the critical points. So this is one way of finding the derivative. Of course, you can find the derivative in the normal classical form as we do the quotient rule. In that case, you would see the denominator something like 6x minus x squared, I think, and you would still have the same 2 points. It doesn't matter by what method you do, as long as you do things correctly. And so you would have 0, 6, but one thing that people tend to forget, 3. We have a vertical asymptote. We have an interruption in this graph. So the derivative has to be found on 4 segments, because when x goes from to the left of 3 to the right of 3, the expression x minus 3 changes sign. So it's important to mark this interruption point, this point that does not belong to the domain, as a critical point as well. Even though the function is not defined, there will be no minimum maximum point, but we have to mark it to get the signs correct. And so if x is very, very large, we have plus very, very small negative number that will be positive. If x is between 3 and 6, for example, 4, then we have 1 plus minus 9, that's negative. Remember that inside each segment, you may choose a value of x to check the sign of the derivative. If x is, for example, 2, that is between 0 and 3, if x is 2, then this is 1 minus 1 squared. So again, 1 minus 9, again negative. And if x is negative, a larger negative or any number negative, we see this is, of course, positive. And we see 1, for example, if we take minus something, minus 100 to the left of 0, then we have minus 9 divided by very large positive. So it is 1 minus something very small. And so we understand increase, decrease, decrease, increase. So we see we have a maximum point. we have a maximum point at 0, 0. That would be at the origin of coordinates. And we have a minimum point at 6 and something. 36 divided by 6 is 12. So now you see why this is not a good idea, because we won't see exactly the graph. So in principle, that's why you should leave all graphing for to the end, because at this moment I was in a hurry. I sketched the asymptotes too soon. I chose the scale rather inconvenient. So let's take a different one. Let's take a different scale. Let's take scale something like this will be 2, this will be 4, this will be 6, and so on. And this will be -2, and this will be 2, 4, 6, and we need 12. 8, 10, 12 for the minimum point. So now the minimum point 6, 12, this one, the maximum point 0, 0. All right, where did the maximum point 0, 0. The vertical asymptote, choosing a different color. Vertical asymptote at 3, x is 3. This is my vertical asymptote. If I use a different color, I can actually draw it as a solid line. Don't make it anything dashed. Although actually sketching on this tablet is easier with a dashed line. And the slant asymptote, x plus 3. All right. And now the graph itself. So how we use all this information to graph. Increase, decrease. This is a minimum. This is a maximum, sorry. And actually it's a horizontal maximum because the derivative is 0. That means the tangent line is horizontal. So it's the graph is horizontal-ish. And then we say, okay, it goes to the asymptote. And it's increasing, and here it goes to the asymptote and it's decreasing. Here on the right hand side of the asymptote, it decreases to the minimum, and then it increases going to the asymptote. I am sketching, this sketch is rough because I did not estimate any other points. We could try. If x is 1, we would have -1/2. If x is 1, -1/2, that's here. That's actually correct. If x is -1, we have -1/4, which would be, okay, more flat, a bit there. If x is 2, 4 divided by -1, we have -4. If x is 2, we get -4. That would be here. Okay, you see, a more accurate thing, a more accurate kind of graphing, and so on. So we could find some extra points to actually make the graph more accurate. And we can also guess about the second derivative from the graph. However, of course, if we want to do it properly, we would need to check the second order derivative. That would be, okay, I need to go to the white pen. That would need to see this. And basically, we would see that on the left, to the left of 3, when x is less than 3, the second derivative would be negative. On the right, the second derivative would be positive. There is no inflection point because you see the function is not defined. So when you are just establishing inflection points, minimum, maximum points, looking at the signs of the derivatives, also pay attention to the fact whether the function is defined at that point or maybe we have a discontinuity. And finally, the last graph for today, very similar to what we had, if not the same, I think. I think we had this, the asymptotes are something that we already had. Let me just check and go back. Asymptotes, we had 9, we didn't have 1. We had 9, not 1. But the asymptotes, of course, can be found in a very similar way. You will see that the asymptotes, in this same way, you will see that the slant as x is y equals x, and there's no vertical asymptote. Because instead of 9 in our function, we have 1. You see how it makes absolutely no difference here. Which means we will save time with asymptotes. So, the domain, evidently, all real numbers. The function is, as we see, it's odd again, because f of minus x is minus x cubed divided by x squared plus 1. That is the opposite of the function value itself. When we replace x by minus x in both powers, we get this. So it's odd. Now the intercepts, the zeros. If x is 0, then y is 0. And if y is 0, then x is 0. So there's one and only one intersection point. So this function passes through the origin. The graph passes through the origin, which many odd functions actually do. If the odd function is defined at 0, then it should pass through the origin. So let's remember the asymptotes while we are at this. Okay, I will just cross this out. Asymptotes. Asymptotes, we know no vertical asymptote, and we have a slant asymptote, which is y equals x. Found exactly in the same way. The only difference that is that instead of 9, we have 1. We had an example like that. So see previous examples with limits, with asymptotes. We don't need to do it one more time because this is the same thing. So I'm trying to save time at this moment. Now the derivatives. The first derivative of the function to establish monotonicity. So we can simply differentiate it. So it's first u differentiated times v not differentiated. Okay. Again, the same. No? Good. Minus u not differentiated, but v differentiated, divided by x squared plus 1 and square again. So the first derivative would be 3x to the fourth minus 4x to the fourth is simply x to the fourth. And here we have 1 plus 3x squared divided by x squared plus 1 squared. So we see we have one critical point. X squared times x squared plus 3 factorized, x squared plus 1 squared. We see that we only have one critical point or stationary point, one and only one stationary point, that is when the derivative is 0. And we see that this is when x is 0. Because x squared plus 3 is never equal to 0, of course. This is always positive. All right. When we check, we see the sign diagram. Okay, something. Okay. The sign diagram, 0. So if x is, whatever x is, we see that both factors are positive. So the derivative is positive and the function is increasing all the time. So it doesn't have minimum, it doesn't have maximum points. That's one thing. Now let's do the second derivative. Second order derivative looks like it is easier to, it is probably easier to differentiate this form before factorizing. So the second derivative, u function differentiated for x cubed plus 6x times times the denominator, all the square with the square not differentiated, minus x to the fourth plus 3x squared not differentiated, times this square. The v function is the square. Chain rule, because it's a composite function. Differentiated means differentiating the square means we do what is it doing? 2 times x squared plus 1, so differentiate the square, times the derivative of interior function, which is 2x. And here we have now x squared plus 1. It was squared and then squared again. Now it's the fourth power. So now what we are going to do is let's divide out x squared plus 1. To simplify things, let's divide out. Let's divide everything. So there are two. This is the difference of two products. Let's divide both terms by x squared plus 1. Divide by x squared plus 1, it leaves simply x squared plus 1 without the square, and divide the denominator by x squared plus 1. It leaves us with a cube of x squared plus 1. And now we can try to simplify whatever we see here. Now we can simplify whatever we see here. So now we have 4x cubed multiplied by x squared, 4x to the fifth, plus 6x squared plus 4x cubed plus 6x. I open these parentheses at this moment. Now minus, opening the other pair. This is 4x. 4x times x to the fourth is 4x to the fifth. And 4x times 3x squared is, of course, again negative, 12x cubed. Now we see that these cancel out. No, too bad. Okay, that's my tablet. The contact is not very good. Okay, these will cancel out. And of course, let's remember that we need now the cube. So finding the second derivative is a bit messy, but it is worth doing because it's good practice differentiation for your midterm too, second midterm examination, by all means. And so we have 4x cubed minus 12x cubed. This is minus 8x cubed. Then we have 6x squared plus 6x. So plus 6x squared plus 6x. Not exactly sure, but I think I did things. I hope I did things right. Definitely. And divided by x squared plus 1 and cubed. And basically we see I can take minus 2x out, and I have then 4x squared plus 3x plus 3. And in principle, we can see already that this longer expression in parentheses, this has a negative discriminant. This has a negative discriminant. It has no roots. It cannot be factorized. So for this, the discriminant is negative. Which means that there's only one critical point. This is always positive. This is always positive, and the denominator is always positive because it's positive number cubed. So basically, the sign is defined only by minus 2x. So the sign of the second derivative depends only on this, because this is positive and this is positive for all x values. So now we see we can. Guess what? No, somebody simply switched on their microphone accidentally, I guess. All right.
So you multiply 6x to x square, right? And here you forget to see.
Signs, no, yes, the minuses, no, yes, minus and minus minus. Okay, that's a bit different because then we have something, and I think yes, actually yes, you're right. There are 3 points. So for this is not true, and this is not true. I will not do the erasing. So yes, because I'm doing it without my notes, I'm doing it from my head. I forgot to take out the minus completely. This is what happens to me, and this is what happens to you too as well sometimes. So the roots of these, the critical points of these, minus 12, 3, 3. There are 2 critical points that I am not, well, in a hurry. Of course, one of them will be positive and the other one will be negative. And then, of course, we have the 0, the third critical point. So this is a critical point, and we have 2 more critical points. I simply don't want to detain you. Otherwise, I would go through everything and find the potential error or no error or anything at all. But at the moment, I don't want to hold you longer than necessary. I am in a hurry to sketch the graph actually. So 0, and here we have x1 and we have x2, the critical points. Now, in fact, we can see that for very large x values, this is negative and this will be positive, because think of a quadratic function ends up for large x values, positive times negative. This will be negative. For very small x values, this will be positive. For small negative x values, again, this becomes positive, but this is negative, so we have a minus. And for large negative x values, we again have positive second derivative values. So this means up, down, inflection points at these 2 points, which I, at the moment, because I'm in a hurry, I'm not finding exactly. But you see the function keeps increasing. So it should look like something like up, down, something like this. And it has an asymptote. So we might already start thinking, so, okay, going, concave up, concave down, concave up, concave down, and it has an asymptote. Let's see what it looks like. The solution, actually, the diagram is, I think, attached to the lecture file. So what we had was the asymptote, y equals x. Let's do a red asymptote. Okay. This is the asymptote. I am not doing a scale at the moment. That's not very mathematically correct of me, but the general idea being that here we have an inflection point, and then we have some other inflection point, but not a minimum point, which is, well, somewhere. And then we have an inflection point, but not a minimum point somewhere else, like an odd function, of course, we have. And so what we see is, in general, and thus there is the graph. So now, going back, no extremum points, no minimum maximum points, only inflection points. So the function is increasing all the time, concave up, concave down, concave up, concave down, which means I put these points, not correctly. These would be the correct points, not these. Somewhere there. The exact numbers are, as I said, in the lecture file where I have provided the solution for this with numbers and everything. And see now what we have. Concave up means to this point, of course, to the left we go to the asymptote, but the graph is concave up. It's rather flat actually. It's rather flat if you look at the exact graph. Then at this point, it has reached the inflection and becomes concave down, still increasing. Then it still increases but becomes concave up. And then still increases and becomes concave down and goes close to the asymptote. So the graph actually looks something like this. The graph actually looks something like this. Without extremum points, it looks as if, well, isn't this a maximum point there? Isn't this a minimum point there? No, it is not. It's only an inflection point. It's only an inflection point somewhere. So it just looks like it is a minimum or maximum, but actually the function is increasing all the time. And of course, there's this one moment where the function of the graph becomes horizontal, but goes on increasing. So this is for the general understanding of how functions are investigated. And you will do the complete